Hello, this is the final project for mechanical design, suspension of a Mars Rover design. For Dr. Calvin Stewart, and this team is the team Intimidators. For this project, we will include an introduction, assumptions, free body diagram, hand calculations, optimization, and conclusions. The exploration of space has been a pivotal matter in scientific advancement in the world. Since the 1940s, when dynamic upgrades to the world-class research laboratories were made in order to aid in war efforts, the advancements to air and spacecraft have put the human race one step closer to exploring the universe past our small atmosphere. Advances to wind tunnels, engine propulsion systems, landing and departure gear, and suspension of craft eventually makes possible the Mars Pathfinder mission, which lands on Martian surface on July 4, 1997. The exploration of any new territory requires a massive amount of precise work and machinery with the capability to withstand any sort of expected territory. Such is the case on Earth, anyway, where thanks to centuries of tireless exploration by a myriad of people across the globe, terrains can safely be assumed and prepared for. Such is not the case on the surface of an unknown planet, millions of miles away from the familiar terrains of Earth. Nevertheless, the need for space exploration demands that investigation of this alien land be done so that we can understand the history of Mars' environment, which can help us better understand and predict the past, present, and future of our own planet. In this project, we will focus on just one of the most integral parts of the vehicle that will be sent to Mars in 2020 to continue the exploration of the planet. The suspension system of such a vehicle must be one of the most sophisticated systems created, for it will be expected to traverse a majority, if not all of the 55.91 million square miles of the surface of Mars. Finding the value and locations of the maximum stress, the fatigue, and yielding of the materials of the rover will help engineers design a system that will maximize the time that this machine can be operated, keeping in mind that manual maintenance will be possible. The mission comes with many restraints. The most obvious ones relate to maintenance and operations of the rover once it reaches the surface of Mars. It also requires considering the possibility of a rough landing, which could damage the rover, or at least diminish its operation. For the purposes of this project, however, we focus only on the following mechanical restraints as we analyze suspension. The angle between the shock absorber and the framing tube does not change. It is fixed at 75 degrees from the horizontal body of the rover. Design life is calculated at 500,000 or 500,000 cycles. The fatigue safety factor is 3. The maximum and minimum load is 850 pounds force and 0 respectively. The diameter is 4 inches and the length is 12 inches. The purpose of this project is to test, numerically and using CAD software, dimensions for the hollow tube of the body of a rover that will meet the required safety factors, keeping in mind the need for an efficient design that minimizes the weight and size without compromising safety. These are free body diagrams of the actual Curiosity rover that was sent to Mars. Figure on the left shows image of the Curiosity rover with a UHF antenna, wheels and DAN labeled. Figure on the right shows an image of the Curiosity rover with a hand, arm, MARDI system, bodies, REMS system, and head labels. Since P1 is on a pin, it is free of any movement, or any moment rather, applied. And since the angle of the force is not changing, P1 is only reacting to the X component of the force. On the other hand, pin 2 or P2 is another pin free of any movement or moment applied to it as well, since it is not really a fixed pin on the X-axis. Taking in account that the wheel on the right side of the diagram is free to move all the way on the X-axis, pin 2 is not exerting any reaction on the Y-axis. This is the reason that pin 1 is supporting any reaction on the X-axis. P2 is only reacting to forces on the Y-axis, since then it is supporting the vehicle under the pulling forces of gravity in the Y direction. For these reasons, the free body diagram will be separated into the reactions using these assumptions. Using this assumption, it was planned to divide the body into two free body diagrams, each of them having different separate types of reactions. Figure number 1 on the left, which only has tension, and figure number 2, which only has bending. The problems arise when attempting to draw the shear and body diagrams. Pin number 2 does not have a reaction moment to counteract the forces, meaning the summation of moments about pin number 2 does not equal 0. For this reason, the model is a wrong assumption and cannot be used. P1 has to have forces in Y to be able to make the summation of moments about 2 equal to 0. These are the handwritten calculations. The PDF is attached alongside the submissions of this project. Accounting for reaction forces in Y on P1 fixes everything in place, and we can then proceed with the project. At the interest point, we don't account for shear forces on the von Mises stress formula, because there is no torsion and because of the shear stress diagram changes direction on the shear diagram, passing through the value 0 at this point. These again are the hand calculations. Once again, at the interest point being because of the maximum moment, we again don't account for shear forces in the von Mises stress formula. Once more, these are hand calculations. These are the hand calculations for fatigue. Once the static analysis has been done and the unknowns have been found, one can use the benefit of technology to solve for the values needed. In this case, we use MATLAB software. A code is created with the forces of interest in the critical point, because once again, an assumption that if the design supports this exact point, the design will be safe on another point on this part. A code beginning with the actual force, maximum moment values, factor of safety, yielding strength is created, solving for the maximum stress allowed for this material with a factor of safety of 3, and a limit is set on line 5. A trial and error procedure is performed labeled tries 1, 2, 3, and 4, trying each time dimensions, these being the outer diameter and thickness, given for standard hollow tubes from the table provided in the lecture textbook. The procedure has to be done starting from the smallest dimensions and increase the dimensions until the maximum stress at the critical point is below the allowed stress. The reason behind that the lightest hollow tube to withstand the given force is to be designed. On the first try, with a diameter of 1 and a thickness of 1/8 of inch, the stress is way above the allowed. As we can see, the max normal stress figured in the image on the right is 5.5083 to the 4th power. For the second trial, with a diameter of 1 inch and a thickness of 1/4 of an inch, the stress is also above the allowed. These dimensions cannot be used. For the second try, we got a maximum normal stress of 3.3264 times 10 to the 4th power. For the third trial, we tried a diameter of 1.5 inches and a thickness of 1/8 of an inch. The stress is also above the allowed. You can see we got a maximum normal stress of 2.3260 to the 4th power. For the fourth trial, where the diameter is 1.5 inch and a thickness of 1/4 of an inch, the stress is finally below the allowed. These dimensions can be used, and the design with these dimensions is approved. The maximum normal stress is 1.3170 times 10 to the 4th power. And the number of cycles allowed is 500,000. The maximum number of cycles that we got is way above that number. As a next step, a second test has to be made to check for fatigue to be able to approve the design. A maximum number of cycles is specified, again 500,000, with a factor of safety of 3. All these values are entered in the code, and using the formula to solve for the maximum number of cycles required, this is what it gives. Entering the known values, which is ultimate strength, endurance strength, and maximum normal stress. Utilizing the appropriate formulas and solving for the maximum number of cycles, we also get a result. The maximum number of cycles exceeds by far the minimum number of cycles required for this part. Obviously, this design can be approved. Looking at the number of cycles seems a little unrealistic, so a more realistic analysis is performed next using the fatigue calculation approach with the endurance limit modifying factors. The process of manufacture is accounted for, this being a hot rolled, or factor of Ka being calculated. Size factor is calculated for a non-rotating hollow tube with its respecting equivalent diameter, retrieving from the formula a value for Kb. The pure axial stress at the critical point for a value Kc is calculated. Values for Kd, Ke, Kf are not specified, so they will be set up as having a value of 1. These values can be changed and plugged into the code to account for those values. A new value of endurance limit is calculated and a more realistic number of cycles is given. On this slide, we have the MATLAB code results. The maximum stress allowed with a factor of 3 in PSI is 16,500. The maximum stress in PSI is 13,170. The dimension selected for this design is 1.5 inches and a thickness of 0.25 inches. Again, the number of cycles required by the standard set for the project is 500,000. The number of cycles achieved with the first analysis is a very unrealistically high number. When we did the calculations with the modified calculations, the number of cycles required again compared to 500,000 yielded a modified maximum number of cycles of 9,583,215. So 9,583,215 cycles. Through a process of trial and error, it was possible to successfully design a suspension system for the Mars Rover that could sustain the required load and fatigue. The first trial yielded a stress that was beyond the safety factor required. Not having optimized this design at that point would have caused catastrophic results. Similar results came out with the second and third trials. Not until the fourth trial, with dimensions of 1.5-inch diameters and thickness of 1.4 inches, did we achieve a stress load that was acceptable. This is the end of our presentation. This has been a design of a suspension system for the Mars Rover. This is the Intimidators team for Dr. Calvin Stewart's mechanical design fall 2017 class. Thank you very much for your attention.